Okay, good morning. So we have started our discussion on velocity measurement techniques in the previous lecture. Today we will continue the same. So in this first we will discuss about one of the simplest method for measurement of velocity, which is known as cross correlation technique. So very first method which we will be discussing is known as cross correlation technique. Okay, so typically if I consider say a signal S1 and its variation with time, say this signal is varying something like this. Now if I consider another signal S2 which is also varying with time and it is also something like this. Now if I take the product of S1 and S2, what will be product of S1 and S2t? In this situation you can see the product will be some signal which will be having larger peak. Is this point clear? Okay. Now in this scenario it was clearly visible that these signals were looking identical, and whenever we have multiplied these two signals, their yes, so their product is also a larger quantity. So that's why I can say at this moment that the products will be giving me some higher value. Okay, now it may happen that in this scenario it was very simple, that it was clearly looking similar. You may find some signal something like this. Now in this scenario, can you tell S1 and S2 are similar? So what we can do, we can multiply S1t S2t plus some factor tau. Okay, now what will be happening? Whenever my tau will be 0, when tau will be 0, what will happen at that time? I am simply multiplying S1t and S2t. Okay, so at this point S1t and S2t both are 0. At this point S1 is positive but S2 is 0. So this product will become 0. If I go further, then at this point this S2 is positive but S1 is 0. So ultimately again their product will be 0. So now when tau is 0, multiplication and sum of their products is equal to 0. Okay, so S1t and S2t is becoming equal to, sorry, it is becoming equal to 0. Now if you keep on varying the value of tau, say some tau 1, tau 2, then what will happen? At some point of time we will see that part of this can overlap with part of this. Okay, once these two parts will be overlapping, I may find some small peak in the signal. Is this point clear? But there will be some tau equal to tau star, corresponding to which both the peaks will be coinciding with each other, and ultimately I may get a very large peak between them. Is this point clear? Okay, so this is some mathematical analysis. It means cross correlation method is some mathematical analysis which tells that whether two arbitrary signals are similar or not. Okay, now this mathematical analysis we can employ in random signals during the multi-phase flow measurements, and with the help of these measurements we can try to determine the velocity of the dispersed phase particle present in the system. Okay, so what I can do, I can have pipe something like this, and in this pipe say I have some laser and photodiode and at other location also I have some laser and photodiode. So this is location 1, this is location 2. Okay. Now if I consider that at some time bubble is passing through this particular photodiode and laser system. So in this scenario, I may get at location 1, my signal with time is, initially it was 0, whenever bubble is passing, corresponding to that, say I have got some peak and then it has fallen and variation of signal, something like this. Okay, whenever the bubble will be passing through second location, again the signal will be coming like this only, but there will be some difference between, there will be some time lag in between this point and this point. Okay, now what I can do, again this variation also is with t and this variation is also with t. So I can say that I will be having some time like 0, 1, 2, 3, 4. It can be in seconds, milliseconds. Let me consider it is in millisecond, and I'll be having the value of S1. It may be 0, 0, 0, 0, 0, and at say some point of time it has become 1. Okay. Likewise for S2 it will be 0, 0, 0, 0, 0, like, and at some point of time it may become 1. Now if I apply cross correlation method over here, what I need to do? I need to first multiply these two, and after multiplying, so say S1 T into S2 T, and after multiplying all the quantities, finally I will be taking their sum. Okay, then in S1, 2 and S2 T, I will see that I will plot this quantity as function of time, and I will try to see if I am getting a bigger peak or not. Okay, then another thing what I can do, I can take a lag, say S1 of t and S2 of t plus 1, t plus 2. Likewise, I will keep on doing. And the situation corresponding to which I will be getting highest peak in my signal, that will be telling that this tau is corresponding to the situation where my signal has become self-similar. Okay. Now, if I have the random signal, and by doing this cross correlation function from the random signal, I can determine the value of tau. And of course, I know this first signal and second signal are taken from location 1 and location 2. And I know the distance between these two locations. If I know the distance between these two locations, tau is the time period which gives the self-similar behavior between the two signals. It means tau is the period which is the time taken by bubble to move from location 1 to location 2. So by just doing this distance d by tau, I can measure the velocity of this particular bubble. Okay. So this type of method is called as cross correlation method. Cross correlation method is having one disadvantage. If one signal is positive, other signal is negative, then product of multiplications can be negative, and ultimately your peak value in the final quantity will be less. So in that scenario, if the nature of the signal is either positive or negative, there it gives some challenges. But if nature of signal is similar, for example, presence of bubble is either giving a positive peak or it is giving a negative peak at all the locations, because if you have both the quantities negative, then also ultimately their product will become positive. Okay, so this will be working in the scenarios where your system is generating the signal with same sign upon the presence of the fluid particle. Is this one clear? So this is what is explained in the form of slides. So we have to, we can say that similar signal is self-similar when S1 will be becoming equal to S2 into T plus tau star. And how to determine tau star? We define this cross correlation coefficient. So this is called as cross correlation coefficient R12 tau, and this is S1t into S2t plus tau, and ultimately this is minus t by 2 to plus t by 2, and we are integrating this with limit t approaches to infinity. What is the meaning? See, why I am doing this integration over capital T? Because whenever we are doing the measurement, if we simply take measurement only at particular time period T, we will not be able to make any conclusion from that signal. Okay, so ultimately what we do at that particular location, we try to measure the or observe the signal for large interval of time. Okay, once we will be observing it for large interval of time, then whatever the duration over which this signal is taken, that duration is our actually capital T. Is this one clear? So that's why integration is just denoted to consider that whatever our individual signal S1 and S2, these are containing data. These data is not any instantaneous random error, but this is the signal acquired for large interval of time period, which will not be leading to any random fluctuation in the signal. Is this one clear? So this is the method. You can see typically location 1 and location 2 are the locations between which we are observing the signal, and at location 1, if epsilon is my signal value and this is T, so you can see this peak is observed once bubble is passing through this, and here peak is observed after certain delay, and delay between these two is tau star. And if I simply calculate the cross correlation function, then, and if I plot it as function of different values of tau, then you will be finding at majority of tau it will be 0. In some range of tau its value will start increasing, and then it will be giving the highest value corresponding to tau star. Okay, so over here in this particular scenario, because this is a theoretical signal which is shown for the sake of understanding, in this theoretical signal it clearly appears us that without doing cross correlation analysis also we can determine the value of tau star. Okay, but whenever you will be going into actual scenario, in your actual measurement, your signal will not be so clear. You may have some variation of signal, something like this. So this type of signals you will be getting. Okay, so there you have to go for the complete analysis using the cross correlation technique. Is this one clear? Now we were knowing d as the distance, and tau corresponding to tau star, our correlation coefficient is highest. So tau star as the time between the two signals once these are becoming self-similar. Okay, so it means that bubble location is whatever time this bubble is taking from location 1 to location 2, that we have measured, and that's how we can calculate the velocity of this particular bubble. Okay, what are the errors associated with this type of measurements? First error is, say this was some liquid slug and our interest was to measure the velocity of this liquid slug. Once this liquid slug has moved from location 1 to location 2, because of the surrounding velocity and the pressure fields, this slug has contracted and it has become only this much. Okay. Now in this scenario, whenever you will be measuring the velocity, it will not be giving you the exact velocity of the slug, but it will give you the velocity of slug plus velocity of deformation of the interface, because ultimately interface has also deformed from this location to this location. Okay, then other thing could be, if I talk about gaseous phase, gaseous bubble present in the liquid medium, then what happens? In the gaseous phase, we know that the density of a gas is a strong function of pressure. Okay, so if at some location 1 I have high pressure, then corresponding to that gas volume will be less. But if at location 2 the pressure has decreased, then I will be having expansion of the bubble, because at low pressure bubble will be occupying more volume. Okay, so in this scenario again this cross correlation technique will be giving you the velocity as velocity of bubble plus velocity of expansion of the bubble interface. Okay, it will not be giving you exact value of the bubble velocity. Then another situation is you have placed some optical probe at location 1 and location 2. So at location 1, this was the crest of the interfacial wave and you are trying to measure the velocity of this crest. But whenever this has moved from location 1 to location 2, this crest has become so small that it is now not making contact with the probe. So in this scenario, what will be happening? Again, we will be having error in measurement of velocity. Okay. Then another situation is, if you again have optical probe, then from location 1 to location 2 when you are going, the trajectory of the bubble has changed. So if trajectory of the bubble has changed, then ultimately it will not be contacting probe 2. So I will not be getting any measurement of velocity. In place of this, if I use non-intrusive method like laser and photodiode method. So in case of laser and photodiode method, whenever bubble is passing through this and passing through this, irrespective of its trajectory, I will be getting some signal. Okay, but with that signal, though I will be able to measure some value of velocity, but I will be having again error. Why error? Because that signal is based on the assumption that bubble is traveling the linear distance between the two measurement points. But in actual scenario, bubble is traveling more distance. So here we will be observing that actual velocity of the bubble will be more in comparison to velocity which we are actually measuring, because actually it has traveled more distance in that time interval. Okay, is this one clear? So these are some of the errors which are associated with cross correlation velocity measurement. So typically sampling rate of the probe, so whatever data you are observing, sampling rate of the probe should be greater than 2u, where u is velocity of the fluid particle and L is its length scale. Okay, so whenever you connect any probe, optical probe or laser diode based system, all these are nothing but the electronic systems. Okay, so in these electronic systems, when we continuously record the data with the time, then we have to supply certain condition, whether we are recording data at every second or every half second or every millisecond. So likewise we can actually select the sampling rate. So what sampling rate should be there? It should be greater than 2u by L, then only your signal will be of good quality to make a good correlation of the velocity. Otherwise velocity measurement may not be correct. Another important point is, if we have to perform the uncertainty analysis, then in measurement of velocity, then delta u by u will be equal to, delta u will be, change in velocity will be u into delta t. Okay, so u into delta t, this will be the distance which will be moved and d will be the distance between the two locations. Okay, now from here you can see that uncertainty in measurement of velocity will be inversely proportional to the distance between the two probes. It means that if two probes are very close to each other, then measurement of velocity will be correct. Okay, will be having less uncertainty. But if two probes are placed at larger distance, then if two probes are placed at larger distance, then uncertainty will be less. But if two probes are placed close to each other, then uncertainty will be large. But one important aspect is, if I place two probes at very large distance from one to another, then the chances of occurrences of the errors which I described over here, these will be more. So it means that from mathematical analysis we get one constraint, that if the distance between the probes is small, then uncertainty in velocity measurement will be more. But from physical configuration we get another constraint, that if the probes are placed very large distance from each other, then what we will be having? We will be having actually chances of errors because of change in trajectory of the fluid particle or because of the deformations at the interface. Okay, so to avoid this, what should be there? There should be some optimal distance between the two sampling locations. Okay, and that optimal distance is typically kept less than equal to 3 to 5 times of the length scale of the fluid particle. Okay. Now let's talk about next technique, that is called as hot wire anemometry. Okay, so hot wire anemometry is a very popular technique, particularly for measurement of fluctuating component of velocity in the turbulent flows. Okay, so if you talk about single phase turbulent flow, then many people use hot wire anemometer for measurement of fluctuating component in the turbulent flow fluid. So it is based on the principle that you have some hot wire and this hot wire is suspended in the fluid medium, and depending upon the velocity of the fluid medium, there will be some rate of heat transfer between the wire and the fluid, and that can be correlated to determine the value of the velocity field. Typically, the wires which are used in this method, these are made up of either platinum or tungsten, and these are having diameters of 5 micrometers and active length of the order of 1 kilometer. Now, can you tell me why the diameter and length of this wire is kept so small? One reason is flow disturbance. Any other reason? One will be related to disturbance of the flow, other will be heat transfer. Yes, so other will be associated because of the thermal inertia. So if you have some if you have some thick wire, what will be happening? There will be some thermal inertia. Okay, because of it will be having some finite value of the thermal conductivity, and because of that finite value of thermal conductivity, transfer of heat from the surface to core will be actually taking time, and that time will be coming as a time lag. Okay, so this heat transfer process within the wire should happen in time scale less than the time scale of fluctuation of the velocity field. Then only this method will be able to give you the correct measurement of the velocity. So that's why the thermal response time of the wire should be small in comparison to the time scale of the flow. Okay, so if thermal response time of wire is more in comparison to time scale of the flow, then ultimately flow will be changing, but your wire will not be responding to the corresponding changes in simultaneous manner. Okay, and we will not be able to make the correct estimates. Is this point clear? So that is another reason these wires are actually kept so small in size. Another important point is we can go up to 5 micrometer, but we cannot keep the wire diameter less than 5 micrometer. Ultimately, because whenever we will be using this method, we will be using Newton's law of cooling for estimating the heat transfer as function of velocity field. Okay, so when we are using Newton's law of cooling, we have to ensure that our Knudsen number should be less than 0.01, because if we go below that, if we go above that, then our assumption of continuum will not be valid, and ultimately fluid medium cannot be treated as continuous. So wire temperature is generally not increased more than 200 degrees Celsius in order to neglect the radiation and free convection effect. So over here we have to understand, whenever we try to design any measurement method, okay, our idea always is to operate that method in such a way so that the uncertainties and errors associated with the method should be least. And these errors and uncertainties will be only least if the number of phenomena involved are less. So if you keep wire temperature within the range of 200 degrees Celsius, then in between the flow and the wire, mainly forced convection heat transfer will be dominant, and any effect of radiative heat transfer and the free convection or natural convection will be actually negligible. Okay, but if you keep the temperatures above than 200 degrees Celsius, then along with that you have to also account for the, along with forced convection, you have to also account for natural convection effects. Okay, and you have to also account for radiation effect. And if you have more number of phenomena involved, it means you have to take into account more number of variables, and you will be having high chances of uncertainties. Okay, so you can see the rate of heat transfer using Newton's law of cooling, because we are considering over here a cylindrical wire of diameter d and length L. So Q will be H A. A for cylindrical wire, A will be pi d into L, because heat transfer will be taking place from all this surface of the wire. Okay, and TW is temperature of the wire minus TF is temperature of the fluid medium. Now, whenever we have this wire, we have to maintain this wire at certain temperature, then only there will be heat transfer. So from here I will be supplying certain amount of current also. Okay, so if Rw is the resistance of the wire and I is the amount of current which is flowing across the wire, and if I assume that I am operating wire in such a way so that the temperature of the wire is maintained constant. What it means? It means that wire is not gaining any amount of heat. So if it is not gaining or losing any amount of heat, then whatever the heat because of electric energy we are supplying to wire, same amount of heat should be dissipated to the surrounding fluid. So that is the thing I have done over here. I square Rw is rate at which electric power is actually coming into the wire, and right hand side is the rate at which heat is dissipated from the wire surface. Okay, we know that in case of forced convection, Nusselt number is some constant times Reynolds number power alpha and Prandtl number power beta. Okay, so if I know the value of C, alpha and beta, I can calculate the Nusselt number, and from the Nusselt number I can calculate the value of heat transfer coefficient H. Okay. Now one important point we have to consider that whenever we have the electric wires, the resistance of electric wire is also a function of its temperature. Okay, so resistance of the electric wire will be equal to reference resistance. Reference resistance means resistance at temperature of TF. Okay, and after that, whatever the deviation from TF is taking place, for that we have one polynomial equation, and with the help of this polynomial equation we can actually determine the value of the resistance at given temperature of the wire. Now from this you can see that if we have to take into account the temperature dependence of resistance, then how many more coefficients are coming? A, B, C. Likewise in this polynomial equation I will be having more number of coefficients. So though these are the theoretical equations involved, but the involvement of these theoretical equations results in large number of coefficients which we need to determine through the calibration process, and this will make our calibration process challenging. Okay, to avoid this, one practical equation is given which is in terms of Rw and I square input power divided by difference of reference resistance and the wire resistance, and this is correlated with the flow velocity using this relation A plus B u power n. So this is the relation which is used in the practical conditions. Okay, now in practical conditions our only interest will be to determine three coefficients A, B and N through the process of calibration. Whereas if you go for at this entire theoretical equation, then you have to first determine C, alpha, beta, and then you have to determine A, B, C, etc. Okay, so number of coefficients will be becoming so high that calibration process will become challenging. At the same point of time, our uncertainties introduced in the measurements will be more. Okay, so that's why this is the practical condition which is considered. Now, how this operate? This practical equation can be operated with the help of two ways. Either by operating the wire in constant resistance mode, or I can also call as constant temperature mode, or by operating it in constant current mode. Okay, so what you can do, you can maintain the constant current in the wire, and while you have maintained the constant current, if you decrease the velocity, what will happen? Convective heat transfer will decrease, rate of convective heat transfer will decrease. So slowly wire will start heating. If wire is starting heating, there will be changes in the resistance. So corresponding to velocity, whatever change is there in the resistance, that will give you the correlation of velocity and the resistance. Okay, so you will be measuring resistance, but ultimately that resistance will be correlated to the velocity field. Okay, in constant current mode, in constant resistance mode, what is done? Resistance or temperature of wire is continuously recorded, and depending upon changes, if any change in the temperature or resistance has started occurring, corresponding to that, corrective action is taken with the help of a feedback circuit, either to decrease or increase the current supply. And whatever the decrease or increase we are doing in current supply, that is correlated directly as function of velocity field. Have you understood this point? So yes, coefficients are extremely sensitive to small changes of the wire conditions, particularly such as wire fouling, etc. Therefore, calibration must be extremely careful, and it should be frequently done whenever you are using the hot wire anemometry. And it can be operated in constant current mode, which measures the change of wire electrical resistance with the help of a Wheatstone bridge. And it can also operate in constant temperature, or it can also be called as constant resistance, because if temperature is constant, then of course resistance will also remain constant. Okay, so here we have a feedback circuit which regulates the current in order to keep the wire temperature and the wire resistance steady. Okay, now out of these two, if you have to use the hot wire anemometry for turbulent situations where dynamic response or the flow fluctuation is significant, it is very rapidly changing with time, which of the mode you will be preferring? If you see, in constant temperature mode, we have a feedback circuit which is changing the current. Okay, so it means temperature is remaining constant, but we have some electronics arrangement which will be changing the value of the current to maintain the temperature constant. Whereas in constant current mode, we have some thermal inertia associated, which will be leading to changes in resistance of the wire. Okay, and we know that always thermal inertia is more in comparison to the inertia of the electronic circuits, because it is very quick to operate the changes in the electronic circuit in comparison to the thermal inertia of a system. Okay, so that's why the dynamic response of constant current mode is always high in comparison to the dynamic response of the constant temperature mode. Dynamic response will be better in comparison to dynamic response of the constant current mode. Okay, so whenever we have to go for extremely fast, rapidly fluctuating flow situations, then we have to operate our system in the constant temperature. Is this one clear? So all these points are actually explained here. Now this is the typical signal of a hot wire anemometer. So here you can see this is the voltage signal as function of time, because ultimately I am changing the current in order to operate it in the constant temperature mode. If I put some load resistance with this current, I will be getting output in the form of voltage. So that voltage I have plotted as function of time. So here you can see there are small fluctuations, then one dip, one dip. So here you can see all these small fluctuations are corresponding to the turbulent fluctuations in continuous phase, and this larger dip in the voltage signal is corresponding to the presence of the dispersed phase. Okay, what will happen when dispersed phase will be contacting? When dispersed phase is contacting, it will be, say you have a liquid and in the liquid gas bubble is flowing. If gas bubble is wrapping the hot wire, rate of heat transfer will decrease. Once rate of heat transfer is decreasing, the temperature of the probe will try to increase if you maintain the current at the same level. So corrective action closed loop system, what it will do, it will immediately decrease the value of the current so that it can meet the rate of heat transfer value. So that's why you will be getting that the presence of the dispersed phase, presence of low conductivity dispersed phase will lead to decrease in the voltage signal. But if you have the reverse situation, what is the reverse situation? That continuous phase is a gas and dispersed phase is a liquid drop. Then what will happen? Drop will increase the rate of heat transfer. So if it will increase the rate of heat transfer, it will try to decrease the temperature. So that's why current has to be increased. So in case of drop, your signal will be something like this. Instead of falling, it will be rising. Is this one clear? Now you can see one important point. If you zoom in into the probe, so D was the diameter of the wire. If you zoom in, you will be finding that bubble will be looking bigger. You will be finding that while bubble is approaching with some interfacial velocity, its interface will be deforming. Okay, and it will be wrapping certain angle at any time t, and of course with the time it will keep on wrapping the more portion, so this value of angle will keep on changing. So typically d theta by dt is considered proportional to dv by dt. Okay, so here you can see this is the voltage signal and it is time. So the slope of voltage signal with time will be representing rate of change of voltage signal with time. This rate of change of voltage signal with time is almost proportional to the rate at which bubble interface actually wraps the probe or wire. Okay, so it is proportional to d theta by dt, and theta, how much this angle it will be wrapping, this is a function of interfacial velocity, delta rho, density difference between the two mediums, and sigma is the surface tension coefficient. Okay, and finally the interface velocity, because what will be interface velocity? Faster is the interface velocity, at faster rate it will be wrapping the wire. So interface velocity is typically given in terms of some constant k into dv by dt. Is this point clear? So with this we will stop for today. So today we have discussed the two methods, cross correlation and hot wire anemometry, and in both the methods one important point you have to consider, we have a single measurement location. So it means that these methods can be employed only for measurement of velocity at some localized locations. Okay, if you have to extend the measurement of velocity for entire flow domain, then we have to go for some more advanced techniques. Okay, so these techniques will be able to give you the measurement of velocity at some specific locations.